Let's explore backtracking problems, an algorithmic problem-solving approach. We'll look at 3 classic examples: the Sudoku Solver, the word search puzzle, and finding a Hamiltonian cycle in a graph. So, what exactly is backtracking? Backtracking is an algorithmic technique used to solve problems recursively. It works by attempting to build a solution incrementally, one step at a time. The key benefits of backtracking are that it explores all potential solutions systematically. It abandons a path as soon as it determines that the path cannot lead to a valid solution. By doing so, it saves time by avoiding unnecessary exploration. Backtracking is particularly useful for constraint satisfaction problems, where the solution must satisfy certain conditions. Let's consider the general algorithm for backtracking. This is a pseudocode implementation, representing the core logic. The function backtrack takes a candidate solution as input. First, we check if the current candidate is a valid solution. If it is, then we simply return the candidate. If the current candidate is not a valid solution, then we generate possible next steps using the function get_candidates. For each next_candidate, we check if it is valid according to the problem's constraints. If it is valid, we recursively call the backtrack function to explore further. If the recursive call returns a result, it means a solution has been found, so we return that result. If no solution is found along the current path, we return none. The key steps in backtracking are: first, define a solution state and validity criteria. Then, start with an empty or initial solution. Recursively explore all possible next steps. Check validity at each step based on the constraints. Backtrack when a path cannot lead to a valid solution. Finally, return the solution once found. Let's tackle our first problem: the Sudoku Solver. The goal is to fill a 9x9 grid with digits such that each row contains the digits from 1 to 9, without repetition. Each column must also contain the digits from 1 to 9, without repetition. And each of the 9 3x3 subboxes of the grid must contain the digits from 1 to 9, without repetition. The backtracking approach to solving Sudoku involves trying a digit in an empty cell. If the digit is valid based on the constraints, then we move to the next empty cell. If the digit is invalid, or if no solution is possible from the current state, we backtrack and try a different digit in the current cell. We continue this process until the entire board is filled with valid digits. Here is a Python implementation of the Sudoku solver using backtracking. The function solve_Sudoku takes the Sudoku board as input. First, it tries to find an empty cell to fill using the helper function find_empty. If no empty cell is found, it means the puzzle is solved, and it returns true. If an empty cell is found, it gets its row and column indices. It then tries the digits from 1 to 9 in the empty cell. Before placing a digit, it checks if it is valid using the function is_valid. If the digit is valid, it places the number in the cell. Then, it recursively calls the solve_Sudoku function to try to solve the rest of the board. If the recursive call returns true, it means a solution has been found, so it returns true. If the placing of the current number does not lead to a solution, then it backtracks by resetting the cell to 0, and tries the next digit. If none of the digits from 1 to 9 lead to a valid solution, it means there is no solution for the current board configuration, so it returns false. Let's move on to the next problem: the word search. Given a grid of characters and a list of words, the task is to find if the words can be found in the grid. Words can be formed by connecting adjacent characters horizontally, vertically, or diagonally. Consider the grid shown here. The word ABC has been found. Now let's discuss the backtracking approach to solve the word search problem. For each cell in the grid, we try to find words starting from that cell. From each starting position, we explore in all 8 directions, that is horizontal, vertical, and diagonal. We use a recursive backtracking algorithm to explore the paths. We mark cells as visited to avoid revisiting them during the same word search. If the complete word is found, we return true. Otherwise, we backtrack and continue the search. Here is the Python implementation of the word search using backtracking. The function exist takes the board and the word to search for as input. First, it gets the number of rows and columns in the board. The nested function DFS is defined to perform the depth-first search. The base case for the DFS function is when the index I reaches the length of the word, which means the word has been found completely, so it returns true. The function checks the boundary conditions. It verifies if the current cell is out of bounds, or if the character in the current cell does not match the character at index I in the word, it returns false. If the checks pass, then the cell is marked as visited by temporarily replacing the character with a hash. Then the function recursively calls itself to explore in all four directions, that is up, down, left, and right. If any of these calls returns true, it means the word has been found, and it returns true. After exploring all the directions, the function backtracks by restoring the original character in the cell. Finally, the main function iterates through each cell in the board and calls the DFS function to start the search from that cell. If the DFS function returns true for any cell, it means the word has been found, and the function returns true. If the word is not found after searching from all the cells, then the function returns false. Let's look into the problem of finding a Hamiltonian cycle. A Hamiltonian cycle is a path in an undirected graph that visits each vertex exactly once and returns to the starting vertex. The backtracking approach to find a Hamiltonian cycle can be described as follows. We start with any vertex as the starting point. We add one vertex at a time to the path, ensuring it is connected to the previous vertex. We check if the newly added vertex is already in the path. If all vertices are included in the path, we check if there is an edge from the last vertex to the starting vertex. If there is no valid next vertex, we backtrack and try a different path. We continue this process until a Hamiltonian cycle is found, or all the possibilities are exhausted. Here is a Python implementation to find the Hamiltonian cycle. The function Hamiltonian_cycle takes the graph as input. It initializes the path array with the same number of vertices in the graph, and sets the starting vertex to vertex 0. The function Hamilton_util is then called. The base case for the recursive function Hamilton_util is when all the vertices are included in the path. It checks if there is an edge from the last vertex to the first vertex. If there is, it returns true. The function then tries to add different vertices at the current position in the path. Before adding a vertex, it checks if it is valid using the function is_valid. If the vertex is valid, it adds the vertex to the path array, and recursively calls itself to solve the remaining path. If the recursive call returns true, then it means a Hamiltonian cycle has been found, so it returns true. If the recursive call returns false, it means the current vertex does not lead to a solution. So it backtracks by resetting the value of path at the current position to -1, and returns false. Let's summarize the key concepts we've covered. The Sudoku solver systematically fills cells with valid numbers, backtracking when constraints are violated. It ensures all row, column, and box constraints are satisfied. The word search finds words in a grid by exploring all possible paths from each starting position, marking cells as visited and backtracking as needed. The Hamiltonian cycle finds a path that visits each vertex exactly once and returns to the start. It gradually builds the path, backtracking when no valid options remain. Key takeaways. Backtracking optimizes search by pruning invalid paths early. It is ideal for constraint satisfaction problems. It relies on recursive exploration of the solution space. The time complexity is often exponential, but it's practical for many problems. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.